Hello and welcome to this video on finding a basis for the left null space of a matrix. So in this video I will define what is the left null space of a matrix, and then after that I'll define again for you, and as I've done with the past several videos I've made if you've been watching, define what it means for a set of vectors to be a basis for a vector space. Because what we're going to see here is that the left null space of a matrix is going to be a subspace of some Euclidean vector space, right? R2, R3, R4, whatever, under standard operations, of course. And then after that, the rest of the video I'm going to be given a matrix, finding the left null space of that matrix, and then a basis for the left null space. And that'll be all the rest of the video. Alright, those several examples. Alright, so to begin, what is the left null space of a matrix? Alright, so suppose we're given an m by n, right, so m rows, n columns, an m by n matrix A. The set of all solutions to the homogeneous equation x, so this is a vector x, a row vector x, times matrix A equals the 0 vector. And again, as a row vector. So we have a 1 by m row vector x times the m by n matrix A equals the 1 by n row vector, which is all components are zeros. Right, that's what makes it homogeneous. You have zeros on the other side of an equation. Right? The set of all the solutions, right, all the x's that make this true, form a subspace of Rm. Right, all these vectors are from Rm. Right, have m components. So the set of all solutions to this equation form a subspace of Rm called the left null space of A. Right, now maybe you can see why it's called the left null space of A. Right? Remember back, again, if you've been watching my videos or if you've seen it before elsewhere, remember just the plain old null space of a matrix was all the solutions of A times x equals 0, where the vector x was on the right side, and it was a column vector. Well, maybe you can see why this is called the left null space, because we're looking for, these vectors I can put on the left of matrix A to get the 0 vector. So called the left null space of A, and it's denoted as, now, the null space of A transpose. Not left null of A or anything like that. I mean, you could write that, I guess. But for short, it's the null space of A transpose. Now, why is it called this? Why is it denoted by null space of A transpose? Well, let's go back here. So if we're looking for solutions to, vector x times matrix A equals the 0 vector, what if I were to take the transpose of both sides? So I have x times A, transpose equals, the 0 row vector transpose. Remember the transpose of a product of two matrices is the transpose of the second times the transpose of the first. They're equivalent. So now I have this equation is equivalent to A transpose times x transpose, which before it was a row vector, now it would be a column vector, equals, and then the column vector with all zeros. So what we're looking for when we're solving this equation, x times A equals 0, we're just looking for solutions to A transpose times y, where y is just the transpose of x. So I could have written x again here, and it would have just represented some column vector instead. So I'm looking for so when I'm looking for solutions to this equation, the x times A equals 0, I'm equivalently looking for solutions to A transpose times x equals 0 or y equals 0. I'm looking for solutions to that equation. So we're seeing here that the left null space of A is the right null space, or the, where I have vectors on the right of A transpose. Now they didn't call it the right null space. Remember, it was just plain old null space. So the null space of A transpose. Right. So the left null space of A is just the plain old null space of A transpose. That's why it's denoted this way, right, because of what I stated down on the left side here. Another way you could state this is that the left null space of A, or the null space of A transpose, same thing, is all the vectors in Rm that satisfy this equation, that A transpose times Y, equals the 0 vector. Right? All the vectors that satisfy that equation. All right. So now, the definition of a basis, which again, if you've been following my videos, watching them, you've seen this page before. Just reusing it. What does it mean for a set of vectors to be a basis for a vector space, right? So given a vector space V, a set of vectors from V, right, S equals V1 through Vn here, vector 1 through vector n, is a basis for V if S spans V, right? So that means V equals the span of S. Every vector in V is a linear combination of the vectors in S, and S is linearly independent. Meaning that if I were to set a linear combination of those vectors in S equal to the 0 vector, the weights would all have to be 0, right, if they're linearly independent. Only the trivial solution would be a solution to that equation. Okay, so again, I've gone over what a basis is many times in many videos in the past, so just know that it's got to satisfy both of those. Alright, so my examples for the rest of the video: I am given a matrix, so a matrix A, and I'm trying to find the left null space of matrix A, which again, when you see this, the left null space of a matrix A, that's just the null space of A transpose. Then we'll find a basis for the null space of A transpose, this left null space of matrix A, same thing. And the way I'm doing this, the way I'm finding a basis for the null space of A transpose is exactly the same way I found bases for the null space of A, of just a plain old matrix, not the transpose. I did a couple videos ago. Again, if you've been watching, there was a video on finding a basis for the null space of a matrix. If you'd like to go back and watch that, or find somebody else who has a video on it if you'd like, or read about it, whatever. Okay, so again, I'm going to show you a couple ways we can go about this, and they're both going to end up giving me the same thing. Remember, we're looking for, so here's A, it's a 2 by 2 matrix, right? 2 by 2, 2, -1, -6, 3 there. What we're doing here is we're looking for the solutions to, vector x times matrix A equals the 0 vector, where, if matrix A is a 2 by 2, then vector x has to be a 1 by 2, a row vector, and then this would also be a 1 by 2. Right, if I multiply 1 by 2 by 2 by 2, I get a 1 by 2. Okay, so x needs to look like this. It would have to be a 1 row 2 column where there's an x1 and an x2, and then times matrix A. Matrix A is this 2 by 2 or 2, -1, -6, 3. And this needs to be equal to the 1 by 2 matrix, the 0, 1 by 2, 0 matrix over here. So like this, 1 row 2 column. So we're looking for value, that's why it's called the left null space. Now I'm going to do it this way, or we could look at that equation I wrote up last with where we look at A, what's the null space of A transpose, and we'll get the same stuff, you'll see. All right, so if I multiply these two matrices together with the variables x1 and x2 here, I have a 1 by 2 times a 2 by 2. I'd get a 1 by 2 matrix where, the first row, first column would be 2x1 minus 6x2, right, for the first row, first column. And then for the first row, second column, I'd have negative x1 plus 3x2, right? and this needs to be equal to the 1 by 2 0 matrix over here. All right. And you see what ends up here. In order for two matrices to be equal, their entries have to be the same, and this leads me to a system of equations. Right? This, as most things do, right, in linear algebra. This leads me to a system of linear equations I need to solve. In order for these two to be equal, I need 2x1 minus 6x2, right, to be equal to 0. That's the first row, first column entries. And then the first row, second column entries, negative x1 plus 3x2, also needs to be equal to 0. Right, in order for this to be a true statement. So what we're going to see here is that solving this equation, right, where I have a vector, a variable matrix on the left, then a matrix, then equal to the 0 matrix, is equivalent to solving this system here. And then we've seen, right, how to write a system of equations as a matrix equation before. And if you're not familiar with that, I mean, I'm hoping you are. I'm assuming you are, because this might not make sense then. But then this system, I could write this system as this matrix equation here. As, the coefficients of x1, 2, and negative 1 down the first column, and coefficients of x2, negative 6, 3 down the second column, then times a column vector with the variables x1, x2, equals, and then this column vector 0, 0. And look at this. All right, so solving this equation, all right, where the variable matrix is on the left of A, is the exact same thing as solving this equation, where the variable matrix is now a column vector, and this coefficient matrix, hopefully you can see that this is A transpose times, and then this is X transpose, and this is the 0 vector from earlier transpose, right? It's everything, it's a transpose of both sides. It's like I did in the previous page where I said, hey, look at this, take the transpose of both sides, you get this back down here at the bottom. All right. So yeah, so we're solving this equation here, and we're finding the null space basically of A transpose, right? So after all this, we're seeing that the left null space, again, the left null space of A is equivalent to the null space of A transpose. That's what all this is doing. All right. Okay, now to solve this system, I'm going to solve this system here for x1, x2. I would set up a corresponding augmented matrix as usual. Right? I prefer. So the augmented matrix for this is where I have A transpose on the coefficients of x1, the 2, negative 1, negative 6, 3 on one side, then equals, and then 0, 0 on the other. Right, so again, in the future examples, here's what I'm gonna jump to this. All right, this will be my shortcut, where I have, again, this is A transpose here to the left of the bar, and we're finding the null space of A transpose. So, and then the right of the bar has just zeros, right, the 0 vector. Now, even after the next example, like I'll write the zeros on the next example, but after that, I'm not going to, because we're going to be performing row operations and putting these things in reduced row echelon form. And when you do row operations, you're going to see that a column of zeros is going to stay a column of zeros. So I'm going to imagine that they're there in future examples. All right, so now in putting this in reduced row echelon form, RREF. Now you can do this on the calculator. This one wouldn't be so bad here because there's only 2 rows, and can you see if I take half of this first row and add it to the second row would be all zeros. So and then I do half the first row, it'd be 1, negative 3, bar 0, and then the next row is all zeros. And here we are in reduced echelon form, right? Every every row, the first non-zero entry is a 1, and those pivot positions are, those leading ones, you have zeros above and below them, and there's only one pivot column here. Okay, so now that I have this in reduced echelon form, look for the pivot columns. Alright, there's a pivot, the leading one, that's in the column corresponding to coefficients of this x1 up here. So x1 is a basic variable, and then the second column is not a pivot column, so x2, or the other variable x2, is free, meaning I can let x2 be whatever I wish. Right? I can replace x2 with any real number I want, and I prefer to replace my free variables with other parameters, other letters that represent real numbers. So you can leave it as x2 if you wish, but I'm going to replace it with the letter t, right, where t is any real number. And then once you replace x2 with any number, then x1, you can find x1, but you can't replace both of them with any number you want. All right, then looking at that first row, we're getting x1 minus 3x2, so minus 3t will be equal to 0. So the value of x1 must be 3 times my choice of t, and the value of x2 is my choice of t. And this row says 0 equals 0, which is okay, right? 0 equals 0 is a true statement. That's fine, you can ignore it. All right, so the solutions here, the solutions to this A transpose times a vector equals a 0 vector, all right, basically describing me the null space of A transpose. The solutions of this is, my vector x, I guess x transpose looks like this, right? x1, x2, because x started off as a row vector, right, way back here. Right, x started off as a row vector, so that's why I'm saying x transpose is this column vector. And x1 is 3 times some choice of free variable t, and x2 is the free variable t. And each of these has the free variable t in common, so I pull that out, t times the vector 3, 1. Right. So here's a description of all the solutions to that equation. Right. So this is telling me every solution is a scalar multiple of the vector 3, 1. So every solution of the equation is a scalar multiple of the vector 3, 1. Okay. So the null space of A transpose, you can write in a couple ways, right? The null space of A transpose, which is this left null space of A, is the set of all the scalar multiples of the vector 3, 1. So some number t times the vector 3, 1, so long as that number t is real. Right? Or you could also say that the null space of A transpose, right, this left null space of A, is the span of the set with the vector 3, 1 in it. Right. Okay. Now you could also write this as a row vector, right? This means the same thing as the span of the set with the vector 3, 1 in it. Right, where because both of these represent the same vector. They just one's written as a column, one's written as a row, but they do represent the same vector, because they have the same components in the same order. Right, they're both from R2, right? They both have 2 components. And this is actually a subspace of R2. Right? I mentioned earlier, you can see that this is a vector space. The span of a set of vectors is a vector space. we could say that the null space of A transpose, or again this left null space of A, is a subspace of R2. Right. And if you did things correctly, this set that spans the space should also be will also be a basis for the space. But we can double check also by looking at it. And the set with the vector 3, 1 in it is a basis for the left null space of A, or the null space of A transpose. And let's think about that. One, it spans the space by definition here, right? Every vector in the null space of A transpose, right? Every vector in this left null space of A is a multiple of 3, 1. So it spans the space, and it's a it's a set with a single non-zero vector. Remember, when you have a single non-zero vector, it's independent. So it spans the space. It's an independent vector. It's the building blocks for that space. It's a basis for that space. Okay. And if you do things correctly, well, when you have your reduced echelon form and when you're solving your system and all that, you should have a pretty good. You should have a set that's a basis for your null space. Okay, now hopefully that looks familiar, right? Finding the null space of a matrix, right? It says we're finding the null space of the transpose. Now, if you want to check, all right, if you want to check, go way back to the beginning here. If you want to check, are these really, is the span of this vector really a solution when it's on the left side here, really part of the left null space? Well, try 3, 1. If I were to put 3, 1 here, 3, 1, you'd have 6 minus 6, 0 for the first row, first column, and then you'd have negative 3 plus 3, 0 for the first row, second column. This would be a solution to this statement. And any multiple of 3, 1, 6, 2, 9, 3, negative 9, negative 3, plug it in here, multiply by the matrix, you would get the 0 matrix back, and you can check that out on your own. Right. Okay, or do with the transpose. Right? Look at this equation here. Take any column vector, take 3, 1, put it in here, multiply these two, you get the 0 vector. Take any multiple of 3, 1, put it in here, you get the 0 vector. All right? So again, solving these equations are the same. These are equivalent equations. One is just the transpose of the other. Right? Both of these is just I take each side and transpose each side, and I get these two equations. These are the same exact thing. I have the same exact solutions. Okay, great. So for the rest of the examples, instead of looking at matrix A, I'm going to start with a matrix called A. But we're going to be asked for, find again the left null space of A. Remember, this is just the null space of A transpose, right? These would have the same vectors in them. All right, so what I'm going to do is try to find solutions to this equation. Now if I want to find the null space of A transpose, we're looking at this equation here. A transpose times some vector when's that equal to the 0 vector? All right, so A transpose. Let me write that in. Now, A is a 1 by 3. So this is from R3 here. 1, 2, 3. A transpose would be a 3 by 1. 1, 2, 3, like this. All right, this is A transpose. So X needs to be now this is a 3 by 1. So the vector X is a 1 by 1. So just a 1 by 1, right? That way I can actually multiply them. And that would give me the 3 by 1 0 vector over here. All right, so I'm solving this equation here. Right. Now can you see that the only solution is x1 has to be 1, right? This would set up the following system. If I multiply these two matrices, a 3 by 1 times a 1 by 1, I'd get a 3 by 1 where the first row, first column would just be x1. Then the second row, first column would be 2x1. And the third row, first column would be 3x1. And in order for this to be equal to 0, 0, and 0, we'd have this system of equations. X1 would have to be 0, then 2 times x1 would have to be 0, and 3 times x1 would have to be 0. So can you see how the value of x1 would have to be 0 and 0 alone? All right, there aren't other solutions here. Because, if x1 0 here, divide by 2x1 0, divide by 3x, x1 has to be 0 for all three of these to be true. Okay. Or you could have gone to the, like I said, this is what I'm going to do after this example. I make the augmented matrix where I have A transpose on one side and then some bar and then the 0 vector on the other. And even after this, I'm not going to write the 0 vector. So I have these 3 zeros over here, and then 1, 2, 3. These are the coefficients of x1 on the left side. Then I put this into reduced row echelon form, which would be very simple here, right? You just, the first row has this leading 1. I multiply it by -2, add it to the second row, multiply it by -3, add it to the third row, and I get all these zeros below it. And again, this column of zeros over here is all the same. And then really look, if you look at this, only the first row tells me that x1 has to be 0. Right? So the solution to this system, right? So the solution to this equation here, right, that A transpose times some vector equals 0, or some vector times A equals 0 on the left, the only solution here is x has to be replaced by the 1 by 1 0 matrix, just the 0 vector, right? From the 1 by just the 1 by 1, and this is from R1, right? And that's it, right? Only the 0 vector. So the left null space of matrix A. All right, so the left null space of matrix A is, again, this null space of A transpose, which is only consisting of the 1 by 1 matrix with 0 in it. That's it. Okay. Then for a basis, I might have, I know for a fact I've talked about this in previous videos. Remember, this is a trivial vector space. This is a vector space, the set with only the 0 vector in it, but it has no basis, right? You might think, oh well, what about the set with the 0 vector, right? That's not a basis because any set with the 0 vector is dependent, not independent. So the left null space here is the set with just the 0 vector, and the basis for the null space of A transpose, the basis for this left null space of A is, the empty set. There are no vectors in the basis for the vector space with only the 0 vector in it, or that circle with a slash through it, but again, this is the empty set. Right, they would say that this vector space with just the 0 vector in it has dimension 0, right? Because every basis is going to have no vectors in it, so don't forget that. All right. Okay. So that one was a kind of a simpler example, right? There's only one vector, the 0 vector, in the null space for the A transpose, or the left null space of A. And I'm just going to keep going with this. Right? Nothing's really changing. Right? So if you recall how to find the null space of a matrix, you're golden here. You just have to remember, when you hear left null space of A, you're finding the null space of A transpose. Alright, so same deal here. Here's matrix A. I want you to find the left null space. Again, I'll write it again. Left null space of A is equivalent to the null, has the same vectors in it, but as rows, as the null space of A transpose, right? But the vectors in this will be written as columns, but they'll have the same representatives of vectors, right? Vectors with the same components in them. All right, and if we're finding the null space of A transpose here, that means we're looking at this equation, A transpose times, some vector is going to be equal to the 0 vector. All right, and I'll write out what A transpose is. Right? A transpose, now this A is a 2 by 3. So A transpose is a 3 by 2, right? The first row is the first column. The second row of A is the second column of A transpose. Times, and this is a 2 by 3 now, right? A transpose is a, oh, sorry. This is a 2 by 3. This is a 3 by 2. My bad, right? 3 rows, 2 columns. So this X here, right, the vector I'm looking for to make the 0 vector has 2 components, x1 and x2. Right, it's got to be a 2 by 1, right? So I'm actually able to multiply these, and this will be equal to the 3 by 1 0 vector, right? The 0 matrix. Right? All right, so as before, right, you could set up a system of equations here and whatnot, but this has the corresponding augmented matrix to it, or coefficients of x1 down the first column, 1, 2, 3, coefficients of x2, 0, 1, 0 down the second column, little bar here, and the 0 equals 0, 0, 0 on the other side. Again, it's just simply A transpose on one side, 0 vector on the other. All right. Okay, and then the next example, I'll not write these and just say imagine that the zeros are there. All right, then we put this into reduced echelon form. Again, very simple to do by hand here. Reduced row echelon form. This leading one up here, that's a pivot position, right? And then I would get zeros below it by -2 plus that, -3 plus that, -3 times row 1 plus row. All right, so I definitely have the 1 and then zeros below it. I wouldn't be changing the first row at all. And if I do that, if I multiply this one by -2 and then add to the second row, you still have a 1 here. And multiplying this by -3 adding it to the third row, you still have 0 there, right? Zeros stacked on top of each other will remain zeros. And then again, all of these will be zeros all the time. And there you go. This is reduced row echelon form for this matrix. And I'm seeing that both, x1 and x2 are basic. They both columns have a pivot in it, have one of these leading ones in reduced echelon form here. So no free variables. And we're seeing from the first row, x1 has to be equal to 0. Second row, x2 has to be equal to 0. So just like the last example, the only solution to this equation here, this A transpose times x equals 0, the only solution is, the 0 vector, where x1 is 0, x2 is 0, right? I'm replacing these guys with 0 and 0. All right, so my left null space. So the left null space of A, which is this null, the same as this null space, has the same vectors as the null space of A transpose, is again only the set with the 0 vector in it. That's it. And if it's the set with only the 0 vector, then the basis for that is empty. All right, just the empty set. You can put it as an empty set of brackets or as this circle with a slash through it. But that's it, nothing more. Right? There are no vectors in a basis for that vector space with only the 0 vector in it. All right, so 2 examples in a row there where the null space of the transpose was just the 0 vector. And my first example had infinitely many. So there's going to be either just the one solution, right, just the 0 vector, or infinitely many for all these null spaces, left null spaces, just like for the regular null space of a matrix back in a couple videos ago. All right, so just a couple more. So here's another matrix. A, and we're trying to find the left null space. And I'll write this every single example, just hopefully, because I find people tend to confuse left null space and null space, and I get that. The words null space are in both of them. Just remember, when you see the word left in there, left null space, you're going to be talking about the transpose of the matrix. So one more time here, and then one more example after this. Well, I'll write it again. The left null space of A is the null space of A transpose. They have the same vectors in it. Just these are written as rows, these would be written as columns, but they have the same vectors with the same components in them. Alright, so if I'm finding the null space of A transpose, that means I'm looking at this equation, solving A transpose times something. And I used y at the beginning of the video. I know I've been using x's here. You can use the letter y and y1, y2, y3 if you want. I don't know. I'm using x1, x2, x3, and so on. You do what you want. Just make sure you're consistent. Equal to the 0 vector. And what does this equation look like? All right. So again, I'm going to write A transpose here. Now this is a 3 by 3. It'll still be a 3 by 3 then. Just first row of the A becomes first column of A transpose. Second row of A becomes second column of A transpose. Third row of A becomes third column of A transpose. And this is a 3 by 3, so the vector x needs to be a 3 by 1. Have x1, x2, and x3 components in it. And a 3 by 3 times a 3 by 1 will be a 3 by 1, so you have the 3 by 1 0 matrix on the other side. Alright, and then this equation here has a corresponding system of equations you could write, and then this corresponding system will have an augmented matrix. Now I'm not going to put the zeros this time, right? I'm just going to put A transpose 1, 2, negative 3, 2, negative 1, 4, 4, 3, negative 2, and just imagine, right? There are zeros over here. I'll draw them here, but never again, right? Imagine there's the equal 0, equal 0, equal 0, right? 1x1 plus 2x2 plus 4x3 equals 0. 2x1 minus 1x2 plus 3x3 equals 0, and so on. And then I put this matrix, this A transpose, into reduced echelon form or reduced row echelon form. Go to the calculator for that. All right. So I got my TI-84 plus here. So second matrix, again, the 83 is very similar. Go to edit. This is a 3 by 3 matrix. I keep the size the same. First row has entries 1, 2, and 4. Second row 2, negative 1, 3. Third row negative 3, 4, negative 2. And since this is the first time I'm doing this on this video, I quit here. And the last thing I put up was reduced row echelon form of A transpose. I don't want that. So second matrix, I just want matrix A. This is the way I entered the matrix in my calculator, right? I entered the transpose in my calculator. So I go over to math up to where it says RREF. Right, not REF, but RREF. I want reduced row echelon form. And then the matrix that I entered, right, matrix, and what I enter is called A here. You could put it in any slot you want, B, C, D. Alright, so this matrix, right, this is A transpose. When I put it in reduced row echelon form, looks like this. So you got 1, 0, 0, 0, 1, 0, and then 2, 1, 0. And then don't forget, you're assuming there's this equal 0, equal 0, equal 0, this bar with a 0 on the other side here. Alright, now just as solving a system of equations, anytime when you put your system in your augmented matrix in reduced row echelon form, you're looking around for basic variables, free variables. The first column has a pivot, one of these leading ones. The second column has a pivot, right, one of these leading ones in a row. So x1 and x2 are going to be, basic variables. And then the third column has no pivot, no leading one in any row. So x3 is what they call a free variable, right? It can take on any real number value I wish. And as I've been doing in a lot of videos, right, I like to replace my free variables with, some other parameter, some other expression that represents any real number. So t here, so t belongs to the reals, right? All right, so from the first row, we'd be getting, x1 plus 2x3, so plus 2t would be equal to 0. And that would lead me to the fact that x1 must be equal to negative 2t, right? You're trying to get every variable in terms of the free variable t. The second row gives me the fact that x2 plus x3, so plus t, must be, again, equal 0. Imagine that's there. And so x2 must be equal to the opposite of t, right? Negative t. And then x3 is t. So I have my solutions. Right? So the solutions of this equation here, right? What vectors can I multiply the transpose of A by to get the 0 vector? The solutions look like this. Every vector there looks like x1, x2, x3, and I'm just going to replace x1, x2, and x3 with what they look like in terms of the free variable t. You have negative 2t, negative 1t, and then x3 is t. You see how each of these have the variable t in common, the scalar t, it's a real number t. I can pull that out. T times the vector negative 2, negative 1, 1. Right. All right, so what we're seeing here is that every solution to this equation is a multiple, a scalar multiple of the vector negative 2, negative 1, 1. In other words, the null space of A transpose is the span of the vector negative 2, negative 1, 1. Right, and I'll write that in here. Right. So the left null space of A which is also, this null space of A transpose is the span of the set with just the vector, negative 2, negative 1, 1 in it. Alright, so I got that. And again, if you've done things correctly up to this point, you should have a basis in this set. This set with the vector negative 2, negative 1, 1 in it is a basis for the left null space. It is a basis for this null space of the A transpose, right? The left null space of A. Right, because first of all, it spans the null space, right? Every vector in here would be a multiple of this vector, as we've seen up here. And it's a set with, one non-zero vector, so it's definitely independent as well. Another thing to say, too, is that the null space of A transpose, right, this left null space of A, is a subspace of R3, right? Every vector in here is from R3, and it's also a vector space in its own right, under the standard operations. All right, so I've got just one more, right, just one more. So here A is this 3 by 2 matrix. The rows, 5, 2, 3, negative 1, 2, 1. And one last time, I'm trying to find the left null space of matrix A, which will have the same vectors, just written as rows, as the null space of A transpose. They'll have the same vectors in them. It's just the vectors are written as rows here. They'll be written as columns here. And if we're trying to find the null space of A transpose, that means we're trying to find solutions to this equation. A transpose times some vector x equals the 0 vector. Right? Alright, so A transpose looks like this. Now, the A was a 3 by 2, 3 row, 2 column. So A transpose is a 2 by 3. So we got 5, 2. First row up here is the first column here, then 3, negative 1. Then 2, 1. Alright, that's a 3 by 2, so then the vector x that we're multiplying by needs to be a 2 by 1, so it'll have two components. It'll be some vector from R2, right, two-dimensional Euclidean space, and a 3 by 2. I'm sorry, a 2 by 3. Oh darn it, I did it again. This needs to be a 3 by 1, doesn't it? This is a 2 by 3, so this needs to be a 3 by 1. It's easier to write them out. All right, so it needs three components from R3. So vector x is going to have three components in it, and a 2 by 3 times a 3 by 1 will be a 2 by 1, right? Give me the 2 by 1 0 matrix here. Great. Sorry about that. All right, so I'm trying to find x1, x2, x3 that make this true. Again, you can set up a system of equations if you wish, but I'm just going to write it'll have a corresponding augmented matrix for the system. I'm just going to write A transpose, 5, 2 here, 3, -1, 2, 1. And again, you're just imagining that there are zeros over here, right? Equals 0 equals 0. I'm just not going to write those after this. Right? All right, so I'll put this into reduced echelon form or reduced row echelon form. I'll go with a calculator. I don't really feel like this. So matrix, and you can do it by hand if you want, with the raw operations. This is a 2 by 3 matrix here. All right, first row, 5, 3, 2. Second row, 2, -1, 1. Alright, and then the last entry I put up was reduced row echelon form for a matrix, so I'm just going to re-enter that, second entry. And there we go, and that looks like some 11ths. I think this might be 5 11ths and 1 11th, -1 11th. Oh, let's change the fraction. Math, change the fractions. There we go. Alright, so we have 1 0 0 1, and then 5 11ths and -1 11th. Alright, and again, don't forget you're assuming there's this little equals 0 equals 0 with the bar and then zeros on the other side, right? Alright, so looking at this, we find our pivot columns, the corresponding to the basic variables. The first column has a pivot, one of these leading ones, and then leading one here, second column. So x1 and x2 again are basic, and x3 is again free. Now be careful. I mean, I know I've shown you some examples here where I think the most number of free variables we had was 1. But just know that there are other examples of matrices out there. When you're trying to find the null space of the transpose, there are some times where you're going to have 2 free variables, maybe 3, maybe 4, maybe more. Okay, maybe no free variables, as we've also seen in this video. Just be careful, right? Just because I'm only giving you examples where there've been 0 or 1 free variables doesn't mean that that's always going to happen. All right, so I'm going to replace x3 with the letter t, where t is any real number. All right. Oh no, not this time. Sorry. Ugh. Look at the coefficients of x3. They have these 11ths in them, these fractions. So just to get rid of those fractions, I'm going to have x3 be 11 times t. So when I replace x3 with 11 times t, that the 11 in this 11t will cancel the 11s here, and I'll have no funky fractions, to work with, and it'll be a little nicer looking maybe. Now you don't have to do this, right? Again, you can leave it as x3 if you want. You can leave it as t if you want. That's fine. All right, so from the first row, I'm seeing that we have x1 plus 5 11ths times x3, but that's 5 11ths times 11t. The 11s would cancel. You just have 5t equals 0. All right, and then the value of x1 would be the -5 times my choice of the free variable t. And then this row here, you have x2 minus 1 11th times x3, but that would just be minus t, right? Again, because the 11s would cancel. And this is equal to 0. And I solve for x2. x2 would be equal to just t. So I have all 3 variables, right? x1, x2, and x3 in terms of this free variable t. So now the solutions of this system, right? The solutions of this equation here, where I'm trying to find the null space of A transpose, right? The left null space of A, same thing. The solutions are looking like this: x equals, and then you have x1, x2, x3, but x1 is negative 5t, x2 is t, x3 is 11t, and again each one of these has the free variable t in common. I pull that out. You have negative 5, 1, and 11. So every solution to this equation is a scalar multiple of the vector negative 5, 1, 11. All right. So the left null space of A, which is this null space of A transpose, is the span of the set with the vector negative 5, 1, 11 in it. All right, every vector in this set, every vector in the null space can be written as a scalar multiple of this one vector. And also again this set with the one vector there, the set with the vector negative 5, 1, 11, this is a basis for the left null space, right? For the null space of A transpose, the left null space of A. Okay, because it spans the space clearly, right? And it's also a single non-zero vector again, right? So it's linearly independent. Great. All right, so a lot going on there, right, with left null space. Now you can set up the equation like I did in the very first example where you had that row vector on the left times the matrix equals a zero vector, and then go from there and set up your system, and then you'll see that that system, when you write the augmented matrix, is just going to have A transpose on the left side, like this here, and zeros on the right. So really, why not just set it up to where you're finding the null space of A transpose, because it is exactly the same thing. They'll have exactly the same solutions, the same set of vectors in them. Just, in one space it's written as rows, and the other space is written as columns, but they have the same components, the same exact solutions. Okay. Great. Now I want to just do at the very end of the video here, this is the last video on all these what are called the fundamental subspaces of a matrix. So I just wanted to do a quick recap on this last page of the fundamental subspaces of a matrix. All right. So the four fundamental subspaces. Of an m by n matrix A. Alright, so suppose you're given m by n matrix A. Alright. These four fundamental subspaces where the column, two of them related to just leaving A the way it was, and the other two were related to A transpose. So one was the column space. Alright, that was the column space of A. And this was the span of all the columns, right? If you looked at every column of A, all the linear combinations of those columns was the column space of A. And this was a subspace of Rm. Rm, right? Every vector in the column space would be a vector with m components, right? If it's an m by n matrix. Then there was the null space of A, right? The null of A. And this was, the set of all solutions to A times x equals 0. Right? And this formed a subspace of Rn, right? Every vector in here had n components, if it's an m by n matrix. All right, then the other two were really closely related to the transpose of the matrix. Right? So the third fundamental subspace of a matrix that we came across in my videos was the row space. The row space of A, which was called row of A. But remember, the rows of A are just the columns of A transpose. So the row space of A you could also have thought of as the column space of A transpose. Right, and this was a subspace of Rn. Right, every vector in here would have n components. If A is an m by n matrix, then the row space has a bunch of vectors that have n components in it. Right. And then finally, the one we just saw in this video, the left null space. Right, which again is just the null space of the transpose. All right, so two of these. So if you're given a matrix, just to find these two spaces, right, column space and null space, leave A the way it is. To find these two spaces, the row space and left null space, look at the transpose, right, and it'll help you out immensely. And then the null space of A transpose, this left null space, is a subspace of Rm. Right, if A is an m by n matrix, every vector in this space would have m components. All right, and keep these in mind. Right, these spaces aren't going to go away anytime soon. In fact, we're going to see there's going to be a topic later on in the course, or later on in these videos. I guess if you're not taking a course and just watching these offhand, in a future video, I will discuss what it means for spaces to be orthogonal and the concept of orthogonality. And it has no meaning right now, maybe, but it will in the future. And what you're going to see is that the spaces that are subspaces of the same Euclidean space. So these two are the null space of A and the row space of A are both subspaces of Rn. We're going to see later that these two spaces are orthogonal spaces. And then later, and then also, not later, but also the two spaces that are subspaces of Rm, right, the column space and left null space, you're going to see that those spaces, those two, are also what they call orthogonal spaces. It's going to be very interesting and a very important result later in the lectures, or later in the videos. All right, so very important, these, given any matrix, and you're always coming across matrices, right, in linear algebra. You've probably seen that a lot, right? Everything we've done, solving systems of linear equations, testing for independence, testing if a set of vectors spans a space, all this junk, right? Looking for null spaces, looking for column spaces, row spaces. All of these involve setting up systems of equations and have a corresponding matrix associated with them. So these four spaces are very important to all these matrices. And again, the concept of orthogonality of the spaces, these pairs of spaces, null space, row space, and column space, left null space, that'll be very important later on. All right, so I hope you have fun practicing in problems, finding the left null space and a basis for the left null space. And thank you very much for watching.